It's a pleasure to welcome Mel Hochster for a talk on research inspired by the work of Karen Smith, which is the perspective. We had just heard the perspective of one of Karen's children. Now we hear the perspective of Karen's dad, academically. All right, go for it now.
Okay. Well, first of all, I want to thank the organizers both for doing the work of organizing the conference and um, for giving me the chance to speak. I suppose as Karen's advisor, I have a unique perspective on some of her work, and say it's a pleasure for me to give this talk. So I want to mention that the slides will be available on what is my new website, United Michigan are in transition. And throughout the talk, well, I won't bother to say this. So I'm going to focus on Karen's research, emphasizing results that I think have influenced the research, inspired the research of a great many other people. And towards the latter part of my talk, I will talk about some work I have done recently with Yongwei Yao, uh, which was definitely in that category. And I don't think even in a week conference, it's possible to do justice uh, to all of the really important work that Karen has done. But I've singled out some of my favorites. And as and I should say I will assume familiarity with tight closure and occasionally other background. Uh, by and large, a lot of what I say will overlap other speakers' talks, but probably for just a minute or two. And I hope it will just be helpful to them, whatever I say that does overlap. So I have the standard notations here, and I'll use a little subscript N sometimes, superscript, I should say. By the way, I have allergies, and I'm afraid I'm going to cough a lot because of that. So this is restriction of scalars via Frobenius. And this is an exact functor. And when R is a reduced ring, uh, this pullback is the same as R to the 1 over P to the N. So if the R is modulo finite over the image of Frobenius, R is called F finite. And these are Frobenius powers. Take the image of the ideal under Frobenius and then extend it. So it's not just the powers, it's the ideal they generate. And if K is perfect, every F on K algebra and every complete ring with residue class field K is F finite. And in the F finite case, this functor preserves finite generation. And for most of this part of the talk, I'll assume that R is Noetherian, characteristic P, and excellent or locally excellent. So I'll remind you that R is weakly F regular if every submodule of every finitely generated module is tightly closed. And this is the notion of strongly F regular, which Kevin has already talked about more geometrically than I will. In the F finite case where it was first defined, and I'm just going to say it for domains now, because it implies product of domains anyway, and it's just a condition on the factors like regular, even though it's defined in the reduced case. So a ring is called strongly F regular if for every non-zero element, there's a positive integer such that the map from R to R1 over P to the 8 splits, but it's not the map that sends 1 to 1. It's the map that sends 1 to the P to the 8th root of C. And because of that, you can hope for a really good ring that you get a splitting if E is big enough. So I'll come back to this, and for the moment, I'm just mentioning the definition. So Karen's thesis, which I'm going to talk about first, and actually throughout, because it's still inspiring recent work, uh, was very important. And I will first mention this theorem. So suppose that R is locally excellent, in theory and characteristic P, and that I is a parameter ideal. And we're not in the local case, so that means that it's generated by part of a system of parameters uh, for all the primes that contain I. And I'm only doing the domain case. You can actually state it reduced also. Then an element's in the tight closure if and only if it's in the extension of I to a module finite extension domain of R. And another way of saying that is that the tight closure is the same as the plus closure of I, where plus closure can also be defined uh, by expanding to the R plus and contracting to R. And here R plus is the integral closure of R in an algebraic closure of its fraction field. So it's the largest, in some sense, the largest integral extension that's a domain. And it's unique to non-unique isomorphism. And that result is very difficult. It's beautiful and important and fundamental. Now, I have to admit that I did I encourage Karen to work on this? No. I was a bad advisor.
No, that's not true. We disagree
Craig
a lot.
Unity and I had tried hard to prove this and failed. So I thought it was too hard to be a thesis problem. Did that stop Karen? You know the answer to that. I should also mention that as a student, Karen asked the most questions and the best questions of any student I've ever had, which I think is still true today. Uh, so I'm going to restrict to excellent rings now, although usually locally excellent suffices. So a ring is called F rational if every parameter ideal is tightly closed. And this is closely related to the characteristic zero notion of rational singularities. So rational singularities, this is highly redundant, but I'll say are Cohn-Macaulay normal. And if you take a resolution of singularities, the higher cohomology of the structure sheaf vanishes. And uh, in working over a field of characteristic zero, and this technique comes up a lot, you can think of R as coming by base change to a field from a finitely generated subring over Z. So A here is a finitely generated Z algebra. And so this is maybe one of the smallest places where the presentation exists. You take the coefficients of polynomials in a defining ideal and throw them into A. And here's another beautiful, important result. So view the K algebra as above, so that A is a finitely generated Z algebra. And then suppose for a Zariski dense open subset of the maximal ideals, that if you take the fiber, that is, if you kill mu, closed fiber is F rational. That's a condition you can put on the algebra so it makes sense for characteristic zero algebras. And Karen proved that R has rational singularities. Another thing that Craig and I failed to do, although I think we conjectured it. And note that for finitely generated Z algebras, whenever you kill a maximal ideal, you are in characteristic P, you get a finite ring. So the rings that satisfy this condition, dagger, are said to have F rational type. And I'll mention that the converse was proved by Nobuhara later. So over the years, many characteristic P properties related to tight closure, which are Frobenius action, have turned out to be close to, at first sight, unrelated notions in equal characteristic zero. And I think Karen's early results in this direction have played a huge role in what's now development of what's now really a branch of algebraic geometry and commutative algebra. So she wrote a paper that was an important step in this direction. And I must say that over and over again, Karen has found deep and unexpected connections between characteristic P ideas and various kinds of singularities and other geometric notions in equal characteristic zero. So coming back now to weak and strong F regularity, weak F regularity has great utility, but there are disadvantages. It's not known to pass to localizations. That's an open question for when you localize at a prime ideal, even for very good rings. Strong F regularity is technical to define. You saw the definition. If you haven't seen it before, I imagine it's hard to absorb during a lecture like this. But as I say, the slides will be available if you want to go back. And by and large, papers are available. But it is preserved by localization, and under quite mild hypotheses, its locus is open. And both facts are quite easy to prove in the F finite case. And I'm going to come back to this point later because there's been recent progress on this, in fact, this week. So it implies at once that every submodule of every module is tightly closed without finite generation. So strong F regularity is strong in that sense. And I'm actually going to sort of sketch the proof of that. I used the wrong. This should be a containment, not a membership. So if you have cu to the q in the bracket q power of n inside, free module is kind of easier to describe without technicalities. So you're taking the qth powers element-wise of all the elements in n and looking at the module they span to get that n bracket q in this case. And when you take qth roots, you get that c1 over q multiplies u into the sort of the extension of n to r1 over q. It's like extending an ideal. If you like, it's the image of n tensored with it. And now, if you just apply an R-linear map sending C1 over Q to 1, so C1 over Q to 1, the coefficients of the elements of N go into R in over here. And you have that for large Q, then you get 1 times U is in N. In other words, N is tightly closed. And that works, as say, without finite generation. And in her thesis already, Karen already saw that every submodule of every module is tightly closed, if and only if zero is tightly closed in every injective hull of a prime of R mod P. And this is equivalent to a condition on the local rings of R. So this is a purely local condition that if you have non-zero C, but now I'm looking at this R is now a local ring of the original R. When for large Q, before in the definition, I talked about having a splitting, but in the case where it's not module finite, that's too much to hope for. But you can hope that the map is pure when you take 1 to C1 over Q for large Q. Because that means that it stays injective, whatever you tensor with, and it's a generalization of splitting that's stable under colimits. So it's very useful. So I say, she didn't publish that part of her thesis as far as, not at the time, as far as I know, but it was a terrific insight. And her point of view, I believe, helped her to prove a very important result with Lubeznik that Kevin already mentioned. So if you have a finitely generated n-graded algebra over an F finite field, characteristic P, and it's weakly F regular, then it's strongly F regular. Uh, Another result that Craig and I tried hard to prove and failed. Uh, and Their proof depends on studying tight closure in graded Artinian modules and using the perspective on strong F regularity that Karen already took in her thesis. So, and I say that it's not essential here that the field be F finite, because if you use later, more general definitions of strongly F regular, then the field does not need to be F finite, like the characterization that every submodule of every module is tightly closed. If you take that as a definition, uh, you don't, that's, this result is true over all fields. And by the way, in case you need something to do in between the talks, this is still an open question, whether weak and strong if regularity are equivalent for all F and K algebras. Uh, the results are in low dimension in the graded case.
Mel, can I point out a typo on your slide? I think you forgot to say graded in the theorem. Oh, it does say graded, never mind. Except I missed it.
Yeah,
Never mind.
but there are
Forget it.
I used the wrong file, so there will be a couple of typos on these slides that I had caught last night, but I somehow messed up when I opened it. So feel free to interject with any typos because there are some, I think. Like I may have misspelled preliminary. That was one I caught last night. Anyway, so another beautiful insight that Karen had is the intimate connection of tight closure with the behavior of differential operators on the ring. And of course, Kevin's already mentioned this. Jack Jeffries will talk about it uh, with much more time than I'm going to take. I'll just going to mention a couple of results. For this and the next slide, R is reduced, characteristic P, again F finite, and I'll also, and I'll recall that F split means that the map R to R1 over P splits as a map of R modules. You can also talk about F pure, where that you only assume that map is pure. But in the module finite case, it doesn't matter. So the next theorem is followed by a theorem that she proved with Vandenberg. So R is called D simple if it's a simple left module over its ring of differential operators. That has a very concrete meaning. The only ideal stable under the action of all the differential operators are zero and the unit ideal. That's a very simple, if you'll forgive the pun, ideal. And ideal. Okay, so let R be F finite. If R is D simple, then for every ideal, the tight closure is just essentially the contraction with respect to Frobenius, just which I've written this way as I expanded to R1 over P to the E and contracted back to R. And then if R is strongly F regular, if and only if it's F split and D simple. So this should tell everyone that differential operators are going to be important in the context of tight closure and other Frobenius studies. Uh, so a bit later, Karen and Michelle Vandenberg introduced the notion of finite F representation type, or FFRT for short, since there's a lot of syllables. And so in this definition, assume R is characteristic P in either complete local or n-graded with R not a field, so that direct sum decompositions are unique, and also that R is F finite. Then R has FFRT. This is the definition or a form of it. Precisely if you take all the Frobenius pullbacks R1 over P to the E, they have only finitely many indecomposable direct sum ends. So the upsisomorphism, of course. And remind you that a ring, and this is not necessarily commutative, is simple if the only two-sided ideals are 0 in the ring. And now the theorem of Karen and Michel Vandenberg is that if you have an F finite ring with these hypotheses, then it's strong and it's strongly F regular, then it has FFRT. Sorry, if it has FFRT, I just misspoke completely. If it has FFRT, then the ring of differential operators is a simple ring, is the theorem. Not what I.
Actually, no, we tried to prove what you just said. We had to put that.
Actually, is there a counterexample?
I think somebody does have one now. Yeah, forget it.
There's a counterexample now.
Yeah.
But it's still open. It's still open for lots of strongly F regular rings. It's not, I mean, it's going to be true a lot of the time, I believe. So it's an interesting question. What additional hypothesis do you need to get that converse? Okay. So Karen, throughout her career, has always sought ways that characteristic P methods could be applied to questions in algebraic geometry. And I'm going to mention a couple of examples. So she has a paper on the Fujita-Freeness conjecture, and the proof works in all characteristics. And the theorem is, if you have a smooth projective algebraic variety, this is over a field of any characteristic. And if L is a very ample for this theorem, line bundle of X, then Kx plus DL is globally generated unless X is projective, D is the dimension of the X, unless X is projective D space and L is the hyperplane function bundle. And in fact, she showed this when X is F rational and under hypotheses a bit weaker than very ample. But the general case is when L is only assumed ample, and that's still open as far as I know, unless there are lots of people here who are more expert on this stuff than I am. But I think that's open, right? Yeah. Nobody's. And it's noteworthy that you can get this result without using resolution of singularities or characteristic zero vanishing theorems like Kadyra vanishing, Grauert, Riemann, Schneider, and the generalizations, positivity results. So again, there's some not really fully understood connection between what you can do with characteristic P methods and what you can do with purely analytic methods. And of course, as Kevin already talked about at great length, another important insight is that she had was the connection between multiplier ideals and test ideals. So here is a theorem from 2000. So let R be a normal Q-Gorenstein local ring, essentially a finite type over a field of characteristics 0. So Q-Gorenstein means there's multiple of the canonical divisor that's Cartier divisor if you think geometrically, or if you like a tensor power, if you work with bundles. So R admits a universal test ideal and is equal to the multiplier ideal of R. And I'm going to put this differently the way she did in the paper. So if you have descent data and good desingularization, then there's a relative multiplier ideal, which is described briefly here. And I'll say a little bit more about it. It has the property that after possibly inverting one element of A, so generically, the image in the quotient by mu, so when you pass through the closed fiber, is a completely stable test ideal for the quotient ring. And so here, this D sub RA is a discrepancy advisor with rational coefficients, and the corner quotes round the coefficients up. And that comes from taking a multiple of the canonical divisor that's a Cartier divisor and pulling it back to the good desingularization and comparing with the canonical divisor and the desingularization. They'll differ by, because you took a multiple, they'll differ by an integer linear combination of components of the exceptional divisor, and then you divide by the multiplier. That gives you a rational discrepancy divisor. Anyway, again, in this context of pioneering the use of characteristic P techniques in geometry, and as Kevin already mentioned, she led the way in the volume dedicated to Fulton with this notion of globally F-regular varieties. Homogeneous coordinate rings are F-regular, and here you don't have to say weakly F-regular or strongly, because all the notions of F-regular agree in the n-graded case by her result with Lubeznik that I already mentioned. So, and in characteristic 0, you can do something comparable by working with rings of F-regular type, where I'll leave you to figure, you've seen F-rational type. I'll let you work that out or look it up. Anyway, and a key point here is that you can prove really subtle vanishing theorems for cohomology using this notion instead of something like Kodaira vanishing. And describing the result in the paper, I'll mention Fano varieties. They're smooth projective varieties whose anti-canonical bundle is ample. They're globally F-regular. But a question was raised for what happens when you let a torus act and you get something that's not smooth anymore, and Karen answered it in this paper. So if you take a quotient by the action of a finite group or a torus on a complex Fano variety, such that it has rational Gorenstein singularities, and if you take an invertible sheaf of OX modules, I said sheep, I don't know. That is, I may have introduced invertible sheep in this lecture. Those who are looking to go to sleep during the lecture, it may be helpful to Nef is non-negative on curves, then the higher cohomology of L is 0 for positive I. Now, I'm going to talk next about a famous paper that Karen wrote with Lawrence Ein and Rob Lazarsfeld. That's been an inspiration for many, and I'm going to, so here's a commutative rings version of their result, and I'm going to just talk about it for prime ideals, although it's not, the paper actually does it for radical and even on mixed ideals and in the generality of sheaves of ideals on smooth varieties over the complex numbers. It's inventiones. So in the commutative rings version, if R is a regular ring finitely generated over the complex numbers and P is a prime ideal of height H, then for all non-negative integers, the Hn symbolic power is contained in the nth ordinary power. And there were earlier results, notably Irina Swanson had a result like this for individual primes, but it came as a very big surprise to a lot of people, myself included, that you could do this uniformly, that there were uniform exponents that did this. So this was an enormous breakthrough. And the proof, the original proof depends on the behavior of something called asymptotic multiplier ideals. I'm not going to have time to talk about it. But I will just very briefly show you a few papers that ensued. And I mean very briefly. There's one with Craig and I did it, another one. And Craig and Louisa Griffo and a bunch of people. This was an exposition of the state of the knowledge. And even mixed characteristic generalizations. Lin Chuan, Carl Schweid did one. And the work continues with, and eventually this led to the notion of diagonally F-regular algebras to attack the problem. And the work on uniform symbolic topologies, et cetera, continues into the present. It's still largely an open question. So I will briefly describe the result that Craig and I were inspired to prove, which we used a completely different technique, but it wouldn't have surprised anyone if Karen had done this, because you can do this with tight closure instead of with basically vanishing theorems that underlie the asymptotic multiplier ideal approach. And you can get the characteristic zero case by reduction to characteristic B. So the result we proved was that if R is an Arthusian ring containing a field of any characteristic, I is an ideal, and H the largest height of an associated prime. So I'm even allowing mixed. And if I has finite projective dimension, then the Hn symbolic power is in the tight closure of the nth power. So you don't need regular. It's one of the many examples where regular can be replaced by finite projective dimension, and you have to adjust by taking tight closure. But of course, if it's regular, all projective dimensions are finite. And tight closure doesn't do anything in the regular case. Everything is tightly closed. So I'm going to briefly mention two results on cluster algebras. There'll be, I think Greg's giving a whole talk on it later in the conference. So I'm going to say this very fast. If you haven't seen this stuff before, I don't know what you can get out of it, but you can listen to his talk and you can go read some papers. Like this paper is a very nice introduction. So cluster algebras are obtained from quivers over a field using seeds. And the seed data includes a quiver with no loops or directed two cycles. And the vertices are put in correspondence with a transcendence base for a purely transcendental field extension, script F. And there's a partition of these variables into, or vertices into, I'm not really distinguishing at this one moment, between frozen and mutable vertices. And the set of variables is called a cluster. But I should distinguish between the variables and the vertices, because you can use other transcendence bases as seeds, many others. So there are rules for mutation into a new seed. And each new seed has a cluster associated with it, a different transcendence basis, where you have a different set of elements on the vertices. And the cluster algebra is generated by all the elements of the clusters that you can recursively generate by mutation. together with the inverses of the frozen variables. And I'm not giving you, for time reasons, the rules for mutation. So given a cluster algebra over a field K, for any cluster, you can associate a Laurent polynomial ring by throwing in all of the variables and their inverses. And you can intersect these over all the clusters. That's the upper cluster algebra. It's a somewhat misleading terminology because it's not the upper cluster algebra is not a cluster algebra, as I, but so a cluster algebra is acyclic if it admits an acyclic seed, which means that there are no directed cycles through the mutable vertices. So you can't go around in a circle through the mutable vertices with the quiver. And so a cluster localization of A is the result of inverting a subset of the mutable variables in a cluster, provided that the result is the same as the cluster algebra obtained from the seed one gets by freezing the variables you inverted. So that's the notion of a special kind of localization. And the cluster algebra is called locally acyclic if its spec is a union of open affines of acyclic cluster localizations. So that was awfully fast, I know. But as I say, if you're interested, and you should be, you can look at the slides and look at Karen's joint paper on this, which is a good introduction to this subject. So the paper contains two results that I'll mention. Every upper cluster algebra is F-split, and every locally acyclic cluster algebra over an F-finite field is strongly F-regular. So you can get the strong F-regularity of many geometrically significant varieties from this result. But again, for time reasons, I'm not going to do more detail than that. And also, I'm sure Greg will tell you more. So I'm now going to talk about two results that Yongwei Yao and I have worked on recently. And they're both inspired in one by earlier work and helped by earlier work of Karen's. So, so I discussed earlier at the outset Karen's theorem that for parameter ideals, tight closure equals plus closure. And Ian Auerbach proved the following extension of Karen's theorem. And there are several results of his that I'm going to talk about. One of them is that if R is F rational, so that all parameter ideals are tightly closed, then whenever the projective dimension of the quotient is finite, n is tightly closed in M. So parameter ideals are examples. In the F rational case, they are regular sequences, and so the quotient is tightly closed. And he proved that even when R is not F rational, if R is reduced and locally excellent and the projective dimension is finite, then tight closure is plus closure. And his proof uses homotopy of maps between Kazul complexes and projective resolution, including the resolution after you've applied Frobenius. So and he proves a stronger phantom version that I'll talk about briefly later. Now, I'm going to talk about a generalization of this, of Ian's result, but it still comes back to Karen's result. So a finite G dimension is a notion introduced by Auslander and Bridger, and I gave a whole lecture on this earlier this year. Here I'm going to be quite brief. It's a significant weakening of the notion of finite projected dimension, and there are references in the bibliography if you want to learn about it. The slides from my talk earlier are available about it. G dimension is also called Gorenstein dimension. And one of the properties is that over a Gorenstein local ring, every finitely generated module has finite G dimension. And there are lots of analogies between the two theories of finite projected dimension, finite G dimension, where if the ring is Gorenstein, like the residue field has finite G dimension, if and only if the ring is Gorenstein in the local case, and so forth. And it's quite a beautiful theory, I think. And in an effort to strengthen Ian's result, but also to get versions that work not just for tight closure, but there are many parallel closure operations now. You'll hear about some of them during the conference. Yongwei and I proved the following result. So I'm going to call a cyclic module regular cyclic if it's the quotient of the ring by a regular sequence. And since the regular sequence can be empty, that includes the ring. And the theorem is that if R is Noetherian of G dimension D, and the G dimension of a module is D, then you can embed the module into a direct sum of regular cyclic modules. So every module of finite G dimension embeds into a direct sum of modules of the form R mod a regular sequence. And you can do it in such a way, in fact, that all the regular sequences you use are initial segments of just one regular sequence if you want to. I don't know that that's so important here. And you can do it so that the G dimension of C is at most D also without increasing the G dimension. And if the projected dimension is finite, and you can also do it with the projected dimension of C being finite. So every module of finite projected dimension embeds in a direct sum of quotients of R by cyclic modules. And so there is a preliminary version of this paper up. It hasn't changed in a long time, but it has changed recently, and the recent results are not yet posted. But there is a more detailed statement in the slides from the Fellowship of the Ring. And Ian's theorem on F-rational rings follows at once. But this embedding theorem gives the same result that when you have tight closure for quotients by regular sequences, you get it whenever the quotient has finite projected dimension. So I'll talk about this abstractly a little bit. How much time do I have? 10 minutes. Okay. So suppose star is a closure operation on finitely generated modules. And I'll use the term star closed for the analog of tightly closed. And I'm going to assume just three things. First, n is closed if and only if 0 is closed in the quotient. That's a property of tight closure and many others. And the closure in a submodule is contained in the closure in the big module. So as you increase the ambient module, the closure can only get bigger. And third, if 0 is tightly closed in each of two modules, then it's tightly closed in the direct sum. So those are fairly mild axioms on the closure. So tight closure, plus closure, solid closure, Frobenius closure, and integral closure, various algebra closures, including big cone Macaulay algebra closures. For integral closure, there are a number of definitions, and you have to pick the right definition, but I'm not going to, I don't want to be sidetracked by that. Extended plus closure, the limb closures that Barghoff Bott and Lynch-Wen Ma and I introduced, many others satisfy these conditions. So the term F rational for tight closure suggests calling a ring star rational if parameter ideals are star closed. So So far as Noetherian and star satisfies these conditions, and every regular sequence is closed, then whenever M mod n has finite G dimension, n is closed. And that's just very easy. The quotient embeds in a direct sum of regular cyclic modules, and in each of them, zero is closed. So just using those three axioms, the proof's immediate from the embedding theorem. And I'll mention, I'm going to skip this slide pretty much, but I will mention that it's also a corollary that if you have a Gorenstein ring, every ideal generated by regular sequences is closed. You can't, oh, I do want to mention that Ian's result works in a case, and we have results in a phantom case as well in a preliminary preprint that we're also working on. And I want to mention that you can't get everything when M mod n has finite G dimension, because in the Brenner-Romansky example, the ring is Gorenstein, so every submodule has finite G dimension. I should have said R submodule. So you can't prove anything that doesn't hold for all submodules of Gorenstein rings, and their tight closure doesn't agree with plus closure in that generality. So big cone Macaulay algebras, there are two kinds. So you can define the closure to be the intersection or the union of the contractions when I is extended to a big cone Macaulay algebra. But if you do it with unions, it's simplest if the class is directed by algebra maps, so that the sum of two of the ideals you get this way will be contained in one you get from a single big cone Macaulay algebra. And you can do the same thing for a closure of a submodule. And you can do it for big cone Macaulay modules as well as for algebras, but I'll stick with talking about algebras here. And they always satisfy those conditions. So if R is a local domain, characteristic P, and is either excellent or a homomorphic image of a Gorenstein ring, R plus is a big cone Macaulay algebra. So in those cases, you can take C to be R plus, and you do get a big cone Macaulay algebra closure. So plus closure is a big cone Macaulay algebra closure. And so over a complete local domain, tight closure is a big cone Macaulay algebra closure as well, it turns out. And we have this comparison theorem. Suppose you have two closure operations. Star satisfies 1 through 3. Hollow star satisfies big cone Macaulay algebra or module closure. And suppose you assume for every regular sequence that the solid is contained in the hollow. Then whenever you have finite projected dimension for the quotient, the solid star closure is contained in the hollow star closure. And that recovers, this generalization recovers Ian's theorem that in the locally excellent reduced case, if the projected dimension is finite, then tight closure and plus closure are the same from this, in this very general context from this embedding theorem. And so in the few minutes that are left, oh, and of course, the proof depends on Karen's theorem. Everything traces back to that. And I think I'm gonna, so you have the corollary. I'm skipping most of the slide because I'm running short of time. If two big Cohn-Macaulay algebras agree on ideals generated by regular sequences, they agree whenever the projective dimension is finite. And that will apply to some of the new closures. So the last thing I'm going to talk about as a result of that Karen proved to answer a question of Janusz Kolar that he wanted this result. So suppose F is a map of Noetherian schemes, Z is closed, Z to S is finite, and F is a coherent sheaf on the complement. And then after a base change to think mainly of the reduced and irreducible case, it comes down to that anyway. After passing to an open subscheme, but retaining the original notation, if J is the open immersion, then these higher direct images are free and commute with arbitrary base change. So this is a very nice result that Karen proved. Because finite morphisms are affine, one can reduce to studying the situation where all the schemes are affine. So I'm going to talk about that commutative algebra result. So assume you have a domain, an A algebra R, a closed set defined by I. And now, for the purpose of studying this problem, it turns out you can complete with respect to I. And then you can map a formal power series ring to R, and you can even reduce to the following situation. Karen does all this in her paper. You have a formal power series ring, and you have the ideal generated by the variables. So a very nice situation. And you can think of F, you can extend it. It's only defined on the complement of I, but it automatically extends to all of spec, and it comes from an R module. And now that cohomology that we were talking about is the same as the local cohomology with the indices shifted by 1. And Karen proves you can localize at one element in A and get all the local cohomology. Now you can even say H naught, which isn't true for the in the geometric case. But for local cohomology, you can get all the local cohomology to be free over the localization. And then its calculation commutes with arbitrary base change on A. So I'm going to talk, as it turns out, very briefly. I'm out of time, but so I'm going to go pretty fast. So Yongwei and I were led to investigate this situation when there isn't any copy of A in the ring. So, but I'm going to focus on the case where the ideal is at least prime of height H, and you can't hope to get free by localizing at one element. But what you can do is, assuming you're in a case with there's a canonical module over the Cohn-Macaulay ring are localized at P. You can define an E, which is local cohomology with respect to P. If you localized at the complement of P, it would become the injective hull. But it isn't the injective hull. You're localizing a certain prime that isn't maximal. But you still get a lot of the conclusions of local duality in this situation. And so by localizing at one element, OW is a multiplicative system that maps onto A. It's not A itself, as in Karen's paper, or onto the complement of A, 0 and A. You can localize that one element. Oh, and you don't really need R to be as good as this. You can take a homomorphic image. So with notation as above, you can localize at one element and get all the factors in the ascending filtration, where you take the annihilators of powers of P, that gives you an ascending filtration in the local cohomology. And then the factors can be made free simultaneously. The G depends on M, but it doesn't depend on I or N here. So we've made an associated graded module of the local cohomology free with respect to this filtration by the ascending submodules killed by powers of P. And so you can't get flatness of A itself, but you do get I'm going to have to skip a lot of this, but you get this condition dagger when you do this, that after localizing one element, if you have a sequence of elements in R that's a regular sequence on all, you can get to it to be a regular sequence on all the local cohomology of a specified module. Now, this notion of problem of extending strong F regularity when R is not F finite, there are two ways of doing it. You can put on this purity condition locally, or you can put it on globally. And I'm skipping a lot of this. But it's an open question whether putting the purity condition on locally, which is called strong F regularity in the literature, is the same as putting it on globally with one exponent, which is called very strong F regularity by Hashimoto and F pure regularity by Dada and Karen Smith in their paper. And there are a lot of partial results. But by proving an upper continuity result for the behavior of an upper semi-continuity result for the behavior of purity exponents, which is stated here, in the excellent Cohn-Macaulay case, the behavior of the purity exponent is upper semi-continuous. So, and really Karen's work played an enormous role in our being able to get a proof of this. And now, and this is the last thing I'm going to say as the official talk, we were able to get two results. That one is that if R is an excellent Noetherian ring of prime characteristic P, then the strongly F regular locus in R is open. And if R is strongly F regular, it's very strongly F regular. You can give a global bound for E. And as far as I know, the fact that the strongly F regular locus is open in general, in the excellent case, is very new. If it's in the literature, we didn't find it. Many special cases are known.
Now, what's your definition of strongly F regular here? Pure? Using purity?
Strongly F regular is locally, you get a purity exponent for every C. And very strongly is what you call F pure regular, a global exponent.
So this for 150, okay.
So that's equivalent in the excellent case. And also the strongly F regular locus is open, period. That's something we proved it without realizing it until this week. So so these new results are really very, very direct outgrowths of Karen's work. And I'd like to thank a number of people for their comments on earlier versions of the slides and or and thanks, Karen, very much for all of your work. And thanks for listening. Sorry, I went over.
Thank you, Mel, for the talk. And are there any questions for Mel? Now is the chance.
I will be around for at least some of the other talks.
Okay, good. So there are more chances, but this is the best chance.
I wanted to make a comment.
Absolutely.
Yeah, I mean, kind of directed at the young people in the audience, because multiple times we were mentioning theorems and saying, oh, this is such a great theorem. At the time when I did those things, I thought they weren't good because, you know, like for example, is tight closure equal to plus closure? We thought that could be true for all ideals. right? So then you prove
Right.
it, or I proved it only for parameter items with single failure. So I see students do this, but really, I see students do this all the time. Well, this isn't that good because I only did it in the Cole-Macaulay case, or I only did it in this case. And I just wanna say, like, that's just how math is, and then later, like the same thing with the FFRT, we thought this was some technical thing, oh, wow, we should be able to do without this, and then it turns out that that's a whole interesting subject, and we really do need it, and yeah, so I just, math is hard and slow, and publish things even if you think they're not that good.
And I second, let me second that. I've had students over and over again feel that what they did wasn't good enough, and it turned out to be incredibly important. Am I still audible?
Yes, you are.
We have one question.
Just when are the slides going to be on your website?
When are the slides going to be on?
Later this today, probably in a few minutes.
Okay, excellent.
I want to just look through them one more time, and maybe Yongwei wants to look through them one more time.
All right. So we're slightly behind schedule, but not very much. So let me take a 5-minute break, and then we have the last half-hour talk before the lunch. So we meet back here in like at 12:15. Okay.